Alright, so in this video I'm gonna be explaining this article about oversmoothing. Oversmoothing happens when, for example, two nodes that are near each other, when you have k layers of neural network, their features are become very similar to each other, so that they become useless. So this article in NeurIPS 2023 is very important. So they try to use random dropping to overcome this oversmoothing problem, which is a fundamental problem in graph neural networks. So graph neural networks are widespread in graph representation learning. Random dropping approaches, notably drop edge and drop message, claim to alleviate the key issue of overfitting and oversmoothing by randomly removing elements of graph representation. However, their effectiveness is largely unverified. In this work, we show just empirically that they have a limited effect in reducing oversmoothing at test time due to their training time exclusive nature. So we show that drop edge in particular can be seen as a form of training data augmentation. And its benefits, the model generalization, are not strictly related to oversmoothing, suggesting that in practice, the precise link between oversmoothing and performance is more nuanced than previously thought. We address the limitations of the current dropping methods by learning to drop via optimizing an information bottleneck, which enables dropping to be performed effectively at test time. So this approach of random dropping is another approach. There are other approaches, drop edge, drop message. I think drop message unifies all of these approaches. Learn to drop learns a mask over the messages each node receives, enabling test time message dropping to be performed dynamically. So this is a very interesting. So we also observed that enabling random dropping at test time will considerably reduce oversmoothing, but this does not translate to improved performance, suggesting that minimizing oversmoothing by itself is insufficient. This motivates learn to drop. In contrast to traditional dropping mechanisms, which apply a uniform approach to information pruning and reduce oversmoothing in a deterministic manner, learn to drop learns a mask. So the foundation of this learn to drop is rooted upon information bottleneck principle. So it seeks a representation Z that is minimally informative about the input X, while simultaneously being maximally informative about the target Y. It allows task-irrelevant information to be discarded while preserving useful information, allowing the GNN to focus on the most salient features of the data. Wow. So the authors, the drop edge and drop method, they propose to directly measure the amount of smoothing. Drop edge measures the difference in Euclidean distance, and one criticism is that it does not distinguish between nodes in the same layer. But this drop message computes a metric over nodes of the same layer, the mean average distance, MAD. Notably, both methods are applied exclusively during training, which raises concerns regarding whether they can address oversmoothing at test time. Generalization to unseen data. While these Training time interventions might help reduce oversmoothing on the training data. Their absence during the test phase can potentially lead to inconsistent behavior on the test data due to increased oversmoothing. If the robustness against oversmoothing is only demonstrated during training and not during testing, it reduces the overall confidence in the model's reliability across diverse environments. So this distinction between training and testing time and its implications remain unaddressed. So we measure this oversmoothing. Measure smoothing is we use mean average distance, MAD. This mean average distance. And more recently, we used Dirichlet energy, so we use this one. And so this is the experimental data. You see measuring oversmoothing in random dropping method models, average over 5 runs. So the Dirichlet energy of this drop edge, you see in blue, is going down Dirichlet energy more dramatically. But if you look at drop message, the drop message is competing with drop edge. And the last one is, of course, they separate train and test, but one can see that the drop message for the training is almost the same across layers. There are many things you can see if you look at these three figures. So we have 128 layers, and we want to analyze the effect of Dirichlet energy on that. So Dirichlet energy will be decreased as the number of layers is increased. So this paper is very experimentally, it's not very analytical. They just try to see the effect of that. But they use information bottleneck. And there are two things, X and Z, Z and Y. And, as many articles, similar to many articles, they apply these variational bounds, and then they evaluated on these important data sets: Cora, Sightseer, Texas, for different layers. For example, for 64 layers, if you look at the vanilla approach, or you can compare drop message, for example, with GraphCon, you see the test accuracy for different models. So the boldened one is the highest accuracy, which is L2D, and sometimes drop message for these data sets. So we investigate the relationship between the random dropping approaches and their ability to reduce oversmooth. Specifically, while drop edge introduces a degree of robustness, its direct impact on addressing oversmooth at test time appears limited. We hypothesize that its effects are similar to data augmentation and support this with empirical results. Drop message has a more pronounced effect, but it is still a training phase technique in response to the difficulty in directly applying dropping methods at test time. We present learn to drop, which decides which parts of the message matrix to keep or discard based on the information's relevance. This approach allows us to leverage the effective dropping at test time in a more informed manner. Learn to drop, like many previous methods, reduce oversmoothing while improving performance. However, this is not a guarantee that the performance improvement is a consequence of this oversmoothing reduction.